So what we saw so far is the fiber product and closed immersion, the locally closed immersion in last lecture. So now the criteria of so you know that the original definition was that when a pre-variety in a condition for a pre-variety to be a variety. So that means condition of separatedness, or in other words, condition of separatedness. Okay. So if you remember the original definition for a pre-variety, suppose X is a pre-variety. So what was it? So point was that if I have two maps F and G, say from if you have two maps, say y minus a point, or if you have two maps F and G from y to x such that F restricted to y minus a point is same as G restricted to y minus a point, then implies F equal to G. This was the original definition of pre-variety, right? And then we saw that this is equivalent of saying that this is the condition of separatedness, that X is called separated. X is separated if this happens. So if you have a fine point punctured disk for example, this is y minus point, you can think as a punctured disk. So from a punctured disk to x, if you have a map, then if two maps they coincide on the punctured disk, then the whole map they coincide on the disk. Right, this was the original definition, that if you have a, so this was, then we saw that this is same as saying the diagonal, you have this fiber product x cross x, x is a variety over k, so you have so you have this map delta x, then this is even a delta x is a closed immersion. So in general, for a pre-variety, this is a locally closed immersion, but if this is a closed immersion, that means that it is one-to-one and the image is isomorphic to a closed subset of x cross x or subvariety. Now we saw another condition. Now the proposition, what does it say? So this is the workable condition, or we will use this to prove that Pn is a pre-variety, Pn is a variety, right? So this is the condition. So what does it says that so criteria of separatedness. Another thing we saw that if it is if X is a variety, and if you have two affine subvariety, affine open subset, the intersection is also affine. We saw this exercise yesterday. The intersection of two affine is affine in a variety. So that will be somehow, that is one of the condition. X is pre-variety, and suppose you have an open cover ui I equal to 1 to n finite affine cover. Then X is separated if and only if ui intersection uj are affine ij equal to 1 to n, and so something to do with the map, right? So it is a closed immersion means what? At the affine level, it's a closed immersion means the opposite at the ring level map, it has to be surjective. That is the condition. So what is ui cross uj? Ui cross uj will be ox of ui tensor ox of uj. So ox of ui tensor ox of uj, this map ox of ui intersection uj. There is a natural map, right? Ui intersection uj goes to ui cross uj. This is surjective for all, right? Now, in general, it has to be for every affine cover, but again, that if you do it for one affine cover, then you can reduce it to the case that. So this is the condition. The proof is quite simple. So, and just what I said now, that it is so consider the diagonal map delta x cross x. Now x cross x is covered by union of ui cross uj, right? Then this is a closed immersion means, so this is closed immersion, and so you have this map ui intersection uj to ui cross uj, right? And the map delta restricted to ui inner. Now you see that ui intersection uj is affine. So you are in the category of affine variety. The product of affine is affine. So this is same as giving a map. So this is equivalent of giving a map ox of ui cross uj. Now not surjective, but a map to ox of ui intersection uj, because you are in affine situation, right? This is equivalent. So now this is a closed immersion if and only this is a surjective map, right? This is a closed immersion. It's same as saying this is a surjection. Right? So this is the criteria. So now we will use this criteria to say that something is not separated. So that means we will give a affine cover and then prove that this is not surjective. So for example, the example that line with double points, example of non-separated. Right, non-separated. So you take x1, x2 to be a1, take u1, v1, the open subset, to be a1 minus point, say 0. Take the identity map u1 to v1 identity map. Now you consider, so if you take this variety x1 union, you glue the, so whenever you have two variety x1 and x2, and on an open set if you have isomorphism, you glue this x1 union x2 with this condition, with this identity map, then what you get is x, right? This point will be doubled. So there are two open subsets. One is this, another one is this, right? One containing the point this and the punctured line, another one is this. Now if you see this, so OW1, so O notation I have to be careful. So this is so one open set is this x1, this copy of A1, another open set is this copy of A2, right? So then OX1 plus X2 to O of X1 intersection X2. They are affine. X1, X2, X1 intersection X2 is affine. So then this is same as Kx1, little x1, say the coordinate ring, tensor Ax2. So this will be Kt T inverse. And the map, the inclusion map x1 intersection x2 to x1, x1 intersection x2. So what is the inclusion map? You take the point T, send it to some T comma 0, or you take a point here T, you send it to 0 comma T. So this is the here under this inclusion, and you check that this x1 goes to T and x2 also goes to T. But this is not a surjective map. But this is not surjective. You can check, you just check yourself, just try to convince that yourself that this is the map. When you do, this is not a surjective. Huh? Yeah, because you are taking identity map, that's why x1 and x2 both are going to T, not going to T inverse. If you instead of here, if you just take the inverse map, if you take here, if you want to V1, if x going to x inverse, then this will be the case. Then this is surjective map, and what you get, the space is P1, and that is separated. So now, so this is a affine line with double origin, line with double origin. This is a non-separated variety. So this is an example. You can see easily, right? I mean, just think, huh? It's a pre-variety. So it's non-separated variety. It's a pre-variety but non-separate. Separated, yeah, variety as separated pre-variety. So it is a non-separated, but it's a pre-variety. I mean, intuitively it is clear, right? I mean, because you have you can take this open set here, and you have two ways of completing this map to the A1. This is the open subset. You take this point out. So now you can embed. You can send this. You can complete this map to two ways. So origin is missing. Origin either you can send it here. So that means it will go here, or you can send it to here. So there are two maps, F and G, which are same on the open subset of a punctured disk. This I call punctured disk, but they are different on the So, this is intuitively it is okay. So, now use the same idea to prove that Pn is separated. So, that means Pn is a variety. So, what you do Pn, you covered this with affine open U0, U1, Un example. And then first of all, this Ui intersection Uj, what you need to prove? This is a affine open cover. You need to prove this Ui intersection Uj is affine, right? But what is Ui? Ui is isomorphic to some An, right? Some psi I map was there. These are affine opens. But now what is Ui intersection Uj? In this, it is xj not equal to 0, right? If you call it, if you identify psi I of Ui, if this An, if you say this is x1, x2, xn, then Ui intersection Uj is nothing but the affine, the open subset xj not equal to 0. So, which is nothing but d of xj. But d of xj, you know, it is affine, because you can embed d of f is any hypersurface, any complement of hypersurface or in affine variety is isomorphic to v of. So, this is isomorphic to v of xj y equal to 1 in An plus 1, right? Or in general, if you take any hypersurface in a affine space, that's isomorphic to a subvariety in An plus 1. So, you increase a variable and then this is an isomorphism.
Complement of hyperplane will always be of this form.
Not just hyperplane, you can take xj to be any polynomial, d of f also. If you take f is irreducible polynomial, say d of f, you can always write it as like d of yf equal to 1. You increase, so this is f is a polynomial in kx1, x2, xn. Then you increase one variable. Yes, and consider the polynomial yf minus 1 and consider 0 set of this. This is isomorphism, right? Just take the affine line A1 and consider this xy equal to 1. It is irreducible, xy equal to 1. So, this is v of this. So, now from this to this, what is the image? You just take this origin out. That is nothing but the x equal to 0. That is the hyperplane. The complement of the what is the hyperplane in a affine line? It's a point, right? So, so this is affine. So, now what you need to check that this OUI. So, now you check. I will not do this. So, all are inclusion map. Check OUI. What is the map you need to figure out from OUI cross OUJ to O of UI intersection UJ. So, OUI. So, if you write UI terms for x1, x2, xn, then this will be k x1, x2, xn, and it will be xj is non-zero, so it will be xj inverse. So, So, you need to figure out what is the map and check that this is surjective. I am leaving it to you that to complete the exercise. Complete it. Okay. Okay, so this is now you know that you have a open subset of a variety is also variety. So, all quasi-projective varieties are now varieties. So, basically we are now in very good shape. We mostly the quasi-projective variety is our most general object what we work with in practice. Okay, we define pre-variety and all, but many crazy things can happen, and mostly whenever you don't take a variety, you always think about this example, that a line with that's the simplest example. So, whenever your variety is not whenever you have a pre-variety which is not a variety, that means which is not separated, you think of this example and try to check if your statement is true or whatever you want to do is true for in this case. Okay. So, this is all about separatedness. Okay. So, I will stop here.